presentation on wind turbine noise production. Our guest speaker is Professor Kondula from School of Mechanical and Manufacturing Engineering, UNSW. Thank you very much.
Oh, thanks, Mattia. Thanks, everybody, for... Sorry, getting out of that light. Thanks for coming to my talk. I'm going to talk about wind turbine noise, how it's produced, and some ways to control it. So I'm from the Flow Noise Group at UNSW, and we do more than wind turbine noise. We do a lot of airfoil noise, bluff body noise, all kinds of noise. And we're even doing supersonic noise, but I can't talk about that tonight. What I'll talk about is wind turbine noise. So a little outline is about what I'm going to talk about. First of all, a tiny bit about environmental noise, and then how wind turbines produce noise very quickly, just the basic mechanisms, and then I'll go straight into how we've measured wind turbine noise in the lab. We've built a wind turbine noise rig, or rotor noise rig. We've done numerical simulations, and from that rotor noise rig, we looked at blade tower interaction noise. So this is a very low frequency noise sources and infrasonic noise sources on a wind turbine. And then we switch in the spectrum to trailing edge noise, which is high frequency noise production above 500 hertz. And I'll end the talk with some recent work that we've been doing on controlling trailing edge noise. Okay, so I probably don't really need to go over this to this audience, but environmental noise is a form of environmental pollution, and so it needs to be controlled. So noise from any source can cause either acute effects, hearing loss, or immediate effects through annoyance, stress, etc. But over long periods of time, results in hypertension, reduces learning in children, and productivity drops in the workplace, etc. And even long term, it can cause health problems. And that's why most of us do what we need to do, is measure and control noise in the community. Okay, so wind turbine noise, well, wind turbines are a source of noise, and they need to be controlled, and there's regulations around it. And there's, so it's a good thing to try and understand how they produce noise and how we can reduce noise. So reducing noise is good for the community around wind farms, but it's also good for producing more renewable energy, and it's also good for the cost of a wind farm. So if you can reduce the noise of each unit, you can put more wind turbines per unit square kilometre. But more importantly, if you can reduce the noise from the tip, you can increase the speed of the turbine and reduce the torque loads on the gearbox and reduce the cost of the turbine exponentially. So there's good economic reasons for reducing the noise on turbines. So this is a turbine sketch, and I'm going to talk about how the aerodynamic environment around a turbine creates noise. So you have a turbine on a tower, it's in wind. The wind approaches the turbine, and it's a boundary layer, an atmospheric boundary layer. So the mean velocity, the average velocity profile, is faster at the top and slower at the bottom. So as the rotors go through that boundary layer, they experience different loads, and those different loads creates loading noise on the turbine. That boundary layer isn't steady like that, it's unsteady. It contains atmospheric turbulence, so the air's unsteady, it's moving around. So that turbulent flow interacts with the moving blades and causes broadband, lower frequency noise. As the blade passes the tower, there's a flow interaction between the tower and the blade. Even though it's an upwind turbine, the old downwind turbines had a very strong wake interaction. But as I'll show, the interaction with the blade and the turbine is different in the upwind turbines, and can create tones at the blade pass frequency and multiple harmonics. And the other very important noise source is the trailing edge, which I'll talk about in a bit more detail later. So if we look at a mock spectrum just to try and describe wind turbine noise in a little bit more detail. If we go from low frequency to high frequency, and here's the level. At the far left we have the infrasonic sources, so we get tones at the blade pass frequency and its harmonics. And then in the low frequency zone there's mechanical noise and this turbulence interaction noise. So these are the big eddies in the boundary layer, this big swirling air eddies, and they hit the blade and they create low frequency noise. And that can extend into the audible spectrum, so above 20 hertz. By how far depends on the spectrum of the turbulence and how the turbine is excuse me, operating. And then above that we get, I've called it audible, but we get the airfoil self-noise spectrum. So that's the turbulence on the blade interacting with itself to create broadband noise. And this is the typical noise source that is heard and is controlled by through modifications to the blade shape and blade trailing edge. Okay, so if we move out to the tip of the rotor blade, so this is just a chunk of the tip and it's moving through space. So you can see this is the atmospheric turbulence and it hits the leading edge. That causes fluctuating lift, fluctuating forces. It creates noise. And then as the flow goes over the blade, it creates a boundary layer, it becomes turbulent. And as that turbulence passes the trailing edge, the unsteady pressure in that turbulence, when it goes from the blocked, the hard surface of the blade to the free surface of behind the blade, a little bit of that energy escapes as an acoustic wave. And because it's turbulent, it's broadband, and so it creates broadband noise. So that occurs right along the blade, but it's only really noticeable at the tip because the tip's where it's travelling the fastest. So there's two noise sources there, the trailing edge noise and the leading edge noise. Okay, this is a little sketch of how leading edge noise or turbulence interaction noise is created. They have turbulent eddies in the flow, and they hit the airfoil, creates a fluctuating lift and noise. Okay, so and the last noise source I want to mention is this blade tower interaction noise. So what's this crazy picture? So if we take a slice through the wind turbine, so we're looking at the top and we cut through, this is the support tower and this is one of the blades, and the blades is passing through the front of the tower, and I've drawn streamlines around the tower. So the streamlines just flow around a circular cylinder, just basic fluid mechanics. So stagnation point there and it flows around here. So as that blade passes through those deflected streamlines, it creates unsteady loads on the blade. But that's not the whole story, which I'll show in some of our measurements. But anyway, that's a low frequency or infrasonic sound source, depending on the size of the turbine. Okay, so what have we done? So we have been lucky enough to get funding from the Australian Research Council to look into wind turbine noise sources, its production, and this builds on a lot of work we've done in airfoil, trailing edge noise, leading edge noise production and control. So one of the big things we did in this project was develop this rotor rig. So it's a 3-bladed rotor rig. It can be run as a fan. We ran it always as a fan, but it is designed to run as a turbine in a wind tunnel. Excuse me. And okay, what's it got? It's got 3 untwisted straight NACA 0012 blades, so 1, 2 and the third one's down here. It's driven by a motor. It has a torque sensor and slip ring, so we can get data out if we need to. And we built a 64-channel microphone array with 64 GRAS precision array microphones. This is a picture at the University of Adelaide anechoic chamber where we did some of the tests that I'll show you today. So we ran this as a fan, we call an unloaded fan, so 0 pitch angle of the blades, and we also ran it at multiple pitch angles as a fan. The thought being that it's very difficult to get this into a wind tunnel and take useful acoustic measurements. Most of the physics of the noise production is the same on a fan as a turbine, and we're using this to validate numerical results, excuse me, and then we can run the numerical model as a turbine and explore those noise sources as well. So we also looked at directivity around this rotor. So this is just a top view in an anechoic room with a tower, rotor plane, and this offset distance. So the rotor diameter is about 1 metre, 1,040 millimetres. The tower diameter is 70 millimetres. And we varied this distance between one chord. The chord is 70 millimetres, the same as the diameter, and 2/7 of that. So yeah, and so that enabled us to get a stronger signal from the tower interaction. And we get the directivity in 5-degree increments. And we used 1/2-inch B&K mics for that one. Okay, so this is where we've set it up here at UNSW in the wind engineering section in the Aero Lab. So we've now built this new array system. So again, we're using the GRAS 40 pH microphones, but we mount them on a perforated panel. And the reason for that is we can put the microphones wherever we like, within reason. It's like a big grid, so we can optimize the shape. So Jeffrey, who's hiding behind there, is setting that up now. He designed that array. So I'm going to show you results from the anechoic chamber and in this wind tunnel working section, but both with no flow. So the numerical simulations, we did CFD of the flow through this rotor system, and Yendru's sitting here did this. So there's a computational domain and the rotor's stuck in the middle. We could have flow through this or not, depending on the situation we wanted. So, okay, it was modelled as we had a rotating inner domain for the blades to spin around, and that's some of the incredibly fine mesh that Yendru put together for this project. So 11 million cells for that grid. So we used the CFD, excuse me, we used the CFD simulation to calculate the noise, and Yendru used an acoustic analogy for that. So that took the fluctuating forces on each blade and the tower, and you could then calculate, using an analogy, you could calculate the acoustics, excuse me, at any observed position that you liked. So, okay, so what did we find? So I'll show you some results. First of all, I'm going to show the rotor rig experimental cases as an unloaded and loaded fan. So it's a fan with 0 pitch and with multiple pitch angles, and then simulation results for the same, but extra ones for the for a wind turbine test case. And the first set of results is for blade tower interaction noise. So this is low frequency noise, and then the second set of results will be for trailing edge noise with the higher frequency noise. Okay, so this is the simulation of the rotor rig. So this gives you an idea of what happens when it runs as a fan. So this is sucking air into the rotor, and these are contours of a parameter that lets you visualize the vortex systems. And you can see this flow creates tip vortices, and they're convected downstream because the fan is sucking air, inducing velocity through the rotor plane. And as the blade passes the tower, and it induces flow, and there's an interaction at the surface of the vortices. As a wind turbine, so if we now keep the fan the same, but now put in a forward velocity, it operates as a turbine. Very similar flow field, where we get a tip vortices being generated by each blade, and then they convect over the support tower. So I should mention this is what we call an unsteady RAN simulation. It won't get all the turbulence spectrum. It's very good at getting the part of the flow at low frequency. It doesn't get the high frequency component. So it's very good for doing the blade tower interaction simulation work. So if we zoom in at the tower, we can see the flow structures. So this is the tip coming around, and behind it is a vortex, and then the vortex hits the tower as it gets convected downstream. So that's as a fan. If we run as a turbine, so this is subtly different aerodynamics. This time we're still getting the same vortex impact on the tower, but we're also getting this big wake structure going past the blade each time. So if we look at the pressure, so what I'm going to do now is look at the pressure field and explain what happens how the turbine creates low frequency noise. So the top one is the unloaded fan, and you can see as the blade, so this is the blade zoomed into that same region, and that black thing. So this is the blade, it's moving this way, this is the tower, and this blue here, that's low pressure around each side of the airfoil. Because it's set at 0 pitch angle, it's the same either side. So as that goes past, these blobs are going to interact with this and create noise. If you turn it into a fan, well then that means this side becomes the suction side of the airfoil, and the other side is the pressure side, and then so you get a higher pressure interaction with the tower. And as a wind turbine, the opposite happens. The suction side, instead of being here, is on this side. So as it goes past, it hits the tower and creates a noise, but of a different character. And I'll show what that means. So if you look, here's a video. That's the unloaded fan. So you can see as the blade, so it goes past the tower, it passes the tower and creates fluctuating pressure loads on the tower. And it's not working. Oh, here we go. Here's the turbine. If you look at the turbine, there's much higher low pressure zone as it goes past the tower. So, what's the actual acoustic pressure looks like? So this is a comparison with an experimental simulation, experimental measurement in the anechoic chamber with the simulation for a microphone at the hub height directly in front of the turbine. So the turbine's going around and it's right in front, and you're getting 3 pulses. So this is phase averaged, so over multiple rotor revolutions. So we've taken out a lot of the the stochastic unsteadiness, and we're just left with this black pulse. You get these 3 pulses every time the blade passes the tower. And Yenju's simulation, it's pretty hard to deny he's not capturing the major physics. So that was very pleasing to see that we can simulate that. So now we want to know what's going on. So what the really surprising thing to us was, because we got the simulation and we're using this particular type of analogy, we can separate out the noise sources. We can separate what's happening at the blades and what's happening on the tower. And the red line is what happens on the blades. So you get this little pulse, and it looks okay, but the major noise source is the tower. So the tower itself is radiating much, much more than each blade, which was a real surprise to us. And it must be true because we're getting such good comparison with our experiment. So the tower itself, as the blade goes past, because there's a distributed pressure load on this blade, there's this potential flow interaction. It just creates a large fluctuating force on the tower, and it just radiates a big pressure wave. Excuse me. So if we look in this frequency domain, we can compare the simulation and experiment. So this is very close. So this is the experiment and the simulation. The peaks match nicely, but because the simulation's on a computer, there's no background noise. So this here is the background noise. Well, that's probably rotor trailing edge noise, which I'm going to talk about later. But this is the background noise of everything that's not blade tower interaction, and the simulation doesn't get that. But it does get the peaks, and because we got the waveform right, it's getting this really interesting phenomenon that this is the blade pass frequency, but the harmonics are much higher in intensity because the waveform looks like that. Because, you know, it's not a sine wave. So that's quite close, this one on the left, to the tower. If you move it away to one tower diameter away, that it's kind of typical of a turbine tip. If you look at a turbine tip under full load, it bends back. It can be around that sort of distance, and you still measure the interaction, but it's a lot lower than the closer case. Okay, so now let's have a look what happens when you have a fan. So one I just showed was for an unloaded fan. So now we put an angle of attack on the fan, and we get a similar sort of good agreement, but there's a little bit of over-prediction. But if you look at the individual components, so the black is the total, and the blue is blades are a bit more stronger intensity, but the tower still dominates. And what's interesting is as you change the angle of attack, you change the relative phase of the blades in the tower. So they can either partially cancel or partially reinforce. But when you go to a turbine, because we've only got simulated for turbine, what's really interesting is, because the pressure now, the low pressure side's on the other side of the blade, everything lines up. So black's total, blue's blade, and red's tower. So even though the tower is reduced somewhat compared with the blade, for the wind turbine, they all line up. So they all reinforce to give quite a strong pulse. So that's quite interesting. So, you know, if you've got a turbine, the blade and the tower are both contributing to the low frequency noise that it generates. So if you look at the directivity how this pulse varies rather around the turbine. So we've got different waveforms at different angles. So we've got the side line with 180 degrees, 135, full on. We've already seen that one. And then off to the other side. You can see how it changes. So on that side, as the blade is going that way, it gives a pulse out that way, and as it retreats, it's a suction pulse, and then you can see how it transforms as you go around. You might notice there's not quite such good agreement off axis, and that's because the thickness noise wasn't modelled in the analogy. But I believe Andrew has modelled that wherever he is, and he got it right. Okay, so as a turbine, this is a fan. I'll go as a turbine, same sort of thing. You get a pulse out one side and suction on the other side, and it transforms as you go around. Okay, so, and this is the directivity simulated around the turbine, and the blue is the contribution from the blades. This is the contribution from the tower, so it's like monopolar. But if you look at that per azimuthal angle of the rotating blade, that's like a dipole spinning around because the force is spinning around the tower. So that's time averaged, and it looks like a monopole because it's circular, but in reality it's like a spinning dipole. So it's quite interesting physics. And you add the two together, you add this blue one and this one, you get this sort of long blob of directivity. But it's pretty monopolar, I think. So how do our lab measurements and computer simulations, are they anywhere close to what happens in the real world? Well, Branko, who designed that rig, by the way, he also has done a lot of field measurements in South Australia around wind farms, and I unfortunately couldn't get his time series data, but I found some other time series data. But I got his spectral data, and this here is what he measures. And look, the time series data is pretty close to what we measure in the simulation. And you get the same sort of harmonic pattern where the BPF is here, that's the blade pass frequency, and then the harmonics grow with time and then drop off. And up here there's some other stuff, you know, it's inside and outside of a home. There's of interest, there's gearbox tones, etc. But what we're interested in here is this one. So on the right here is some European measurements by people worried about infrasound affecting seismic monitoring stations for nuclear. You know, they're monitoring the world in case somebody sets off the bomb. So they have very sensitive instruments, and there's some wind farms around them, and they need to filter out their contribution to the measurements. So they did a lot of these measurements, and this here is their infrasound time series measurement, just raw data. I don't think it's filtered in any way, and it's equivalent to having a microphone on the 0 degree size in our experiment. So you'd expect this strong pulse downwards. So we're quite pleased to see that it looks somewhat similar to what we have in the lab. And their power spectral density is much peakier than ours, but that's probably because the frequency resolution is very, very fine. Okay, so that's the low frequency side of things. So I'm going to shift gears now and talk about high frequency stuff. So this is how rotor blades create noise themselves. So the flow travels over the blade, it goes turbulent, interacts with the trailing edge, and creates this thing called trailing edge noise. So this is an experimental beamforming measurement where we've done localization in time and matched it to blade position. So we can measure the blade position with an encoder in the torque sensor, and we can you know, do some signal processing and this is what we get. So as expected, the noise is predominantly from the tip region, and because that's where it's going the fastest. And as it passes the tower, you get this flash, and I believe that's a reflection from the tower plus some sort of mechanical response of the whole system at that frequency. So that was at 2 kilohertz. So we go to 4 kilohertz. We're starting to see the noise source being more clearly defined, and jump straight to 11 kilohertz. Because this is scaled, these frequencies don't correspond to what you'd see in a large turbine case. So it's probably about 8 to 10 times higher than for the same sort of conditions. But anyway, at 11 kilohertz, you can clearly see this is the brightest spot, and that's trailing edge noise. We also get this interesting spot at the leading edge, and that's the tip vortices being formed over it's a square tip. You don't normally have a square tip, but it's a tip vortices forming over that. It creates a bit more noise. And we can even image up to nearly 19 kilohertz. And at 19 kilohertz, that tip, that leading edge noise source is very intense and quite prominent. So Zeb Prime, who did these acoustic measurements, called that the flaming turbine, because it looks like it was on fire. So, okay, so how do we know what the predominant noise source is from about 2 kilohertz upwards? Well, we modelled the noise source using this NASA model called the BPM model for trailing edge noise, and we showed, we've got a paper on it, but we showed pretty conclusively that from about 2 kilohertz up, it's trailing edge noise because these are the third octave band levels, and that's what you'd predict from this special model for that rotor blade, and it works quite well. And even in all angles, the dots are the measurements, and the squares, not squares, the crosses are the predictions, and in most cases it matches pretty well. So we know we've got trailing edge noise working on that rotor rig. So now that we've got trailing edge noise on there, we think, well, great. Now we know when the noise is coming from. Let's do some clever things to try and reduce it. So, so how do we do that? Well, we go back to first principles, and this is my crazy diagram about trailing edge noise. So this grey box, or grey rectangle, that's my idealised airfoil. So just think of it as a semi-infinite plate that goes forever to the left, and there's an edge here. This sine wave on top, that's the boundary layer. So the boundary layer is full of pressure waves. So if we take one wave number, we can model it as this sine wave of pressure moving to the right. So it's convecting along. And when that goes over the edge, this high pressure pushes around this way and creates an acoustic wave, and this way and a rarefaction wave, pressure wave this way, expansion wave that way. And that's trailing edge noise. Because it's turbulent, there's, in real life, that sine wave's a mess of all wavelengths and it's all random. But to help me think about what's going on, I just try and think of one case going over that edge. So then you think, okay, so the problem is this, how this is generating this pressure wave. How can we damp that out? So not just me, a lot of people are looking at porosity and elasticity at that trailing edge. So if we make the edge porous, or if we make it absorbent, have some sort of impedance that's not going from fully blocked to free, we can smooth out that transition from the sharp impedance change to more gradual, and we won't be as efficient as generating these acoustic waves. And a lot of this has come from looking at owls. So it's been a topic for a few years now, where we all know these particular types of owls fly incredibly silently, and we think it's because of the wings, and the wings have all these features. They have this leading edge comb, they have a velvety coating, and they have what we're interested in is serrated and poroelastic edge. So the edge has got a serrated shape, so it does that, and it also is simultaneously porous and elastic. And so Justin Jaworski, when he was at Cambridge, he did this really groundbreaking piece of work where he looked at poroelasticity at the trailing edge of airfoils and developed this theory, and this is his main result. It shows noise reduction versus frequency for one case. So this line here is a rigid porous edge. This one's an elastic edge. You put them together and you get more noise reduction. But the key thing he found is if you play around with the amount of porosity and the amount of elasticity, you can control this curve and make it go up and down. So that's promoted a lot of experimentalists to start playing around with porous and elastic materials to see if we can control this edge. So that's what we've been doing. So this is at the top here. This is a schematic of our anechoic wind tunnel here at UNSW. So it's not to scale. We have a contraction. So, I should start here. There's a fan that sucks flow in here. We actually have a big muffler here that's not shown. And it sucks air through here into the anechoic room, and we test in the open jet. Down the bottom, this is a photograph of inside here for a tests I'm about to show. So this is Chao Yang's work, a PhD student of ours. So here's a NACA 0012 airfoil. So that distance from there to there is 455 millimetres. And this is a 200 millimetre chord airfoil. And we put edge extensions on here of different types, and I'll show you what they are in a minute. This is a small microphone array that we use to image the noise source at the edge and work out if it's doing what it should do. And Chao Yang was very diligent and put a laser vibrometer, so that's what that red dot is, and he monitored the vibration of that edge as well. So he's been testing like crazy. You can't believe how many tests he's done. But this is some of them. I'm not going to show all of them. He's tested, this is a baseline, this flat. So what he used 3D printing. He used 3D printer to produce all these things. 3D printing's great. You can produce crazy designs very quickly. only limited by your imagination. So this is a baseline, so everything's compared to this straight, normal edge. This is the all-porous design. This is to test the theory from Cambridge. So this is very similar to how they model the poroelastic edge. He tried these are serrations that are typically used today on turbines. He tried this called iron serration. It looks like a feathered edge. And then he tried these different designs with different, this is slitted serration, so they're tiny little slits of serrations. He's done sort of this design with pores and solid in serration-like design and changed the wavelength, put slits and pores together. So there's a lot of data. I'm not going to show all of it. I'm just going to show a couple of these ones. Just give you an idea of what's, this is pretty new actually. So using the beamformer, this is an image of the trailing edge. So this is the airfoil from side on. It flows this way. And this here, this blob, that's the trailing edge noise. And what we can do is just integrate around there and just get the noise from the trailing edge. This is the noise from, this is some extraneous noise from the inlet of the tunnel. We can just get rid of that and just look at trailing edge noise. Okay, so what's the type of results you get? So how to interpret this? These are third octave band spectra. That's not labelled correctly. It's third octave band. And so this is the all porous design that the theory guys used. And how to interpret these charts. This is the baseline. And the red is the measurement of this design. Grey means noise increase. White means noise reduction. So the all porous design is not very good because they didn't model scrubbing noise. So as the flow goes over the top of these holes, they create lots of turbulence, and that turbulence radiates away quite efficiently, and that's why we get massive noise increase at high frequency. So while it works a bit here, it's not so good up here. And okay, so this is the slitted serrated. Again, that didn't work very well. Too many pores. It's too thin for the pores to be very well. It's too thin for the damping, the dissipation in the pores, to overcome the extra turbulence generated by the pores themselves. So you're getting noise increase over most of the frequency range. This is a vibration response. I honestly haven't spent a lot of time interpreting what these mean, but you're getting more vibration when the noise is louder. That's what we're seeing on there. Okay, so some designs that actually do work. So these are the best trailing edge serration designs that we've tested. They work pretty well. So these are the iron shapes. So not the normal triangular shapes that turbine manufacturers use a lot, but I reckon they can't not be using these in the near future. So you're getting a reasonable noise reduction between here. There's something funny going on at this frequency, so I would ignore that. But in here we're getting pretty good noise reduction and no high frequency increase, which is good. What is this? This is a slitted serration, and there's reasonable, there's 3 to 5 dB at higher frequency, which is nice. So maybe a good combination would be this and this, but we haven't got up to that yet. The vibration response is not working. So, okay, so these ones here, these are blade extensions that are very thin. So they're sort of add-ons. So that's what they do on turbines. They get an add-on extension, they whack it on and get some noise reduction, and it's good. But what we are looking at now is how can we integrate more novel porous structures into the blade itself. So now 3D printing now, we can actually print an entire rotor blade for that rotor rig that I showed you. So 0.5 metre size, and we can have whatever porosity we'd like in the edge. So one approach that we've done is think of different porous structures, make impedance tube samples, so we print them at a special, I'll show you what they are, and we test their acoustic impedance and come up with some sort of empirical model of the acoustic impedance, or the absorption rather, of that design. And then if we think it could be effective, we print a rotor blade. This is a rotor blade tip, but we do whole blades, and we print that porous structure directly into the blade. So there's no need to have an add-on, because the add-ons add drag, they reduce lift. So the idea is by integrating it directly, we can get a much better performance and reduce the losses. So let's just look at this one. This is a typical sample, very simple sample, and we have only really done simple samples to date, where we just have porosity through holes in plastic 3D printed parts. We've done loads of different porosities, so from solid reference, this aluminium that's very, very porous and doesn't do anything. And then we have different thicknesses to change the porosity, the aspect ratio, and a bunch of other parameters that I could go into, but I'll just show you some of the interesting results. So the good thing about 3D printing is you can do things like put subsurface cavities in. And I think that's the key to getting this thing to work. Not that we've proven it yet, but so by putting in a subsurface cavity, as opposed to just having porals, we can change the sound absorption coefficient. So this is the sound absorption versus porosity for this type of design, and it varies a bit, but if you start putting in cavities of different thicknesses, you can start moving around this absorption region. And it turns out, and we probably should have realised this before, if you make this very fine porosity at the top and then have a reasonable air gap, you can get very good broadband absorption in that 3D printed sample, which is just what you need for an airfoil. So we tested this for a couple of different test cases, and I'll show you just one of them. So we put it again on the rotor rig. This is in the wind engineering test section, but just as a fan with our new array. And instead of that actual test, this is the test I'm going to show you. So I'm going to compare solid aluminium blades and then the identical type of blade, but each one 3D printed with porosity as trailing edge. Now, there we go, that's it running. So up the top there is a CAD image of what we did. This is just a very simple test case, just to really prove that we can do it. So we basically printed porosity different aspect ratios into the trailing edge, did it on 3 blades and compared it. And these are the beamforming images. So on the left, this is a solid blade at 3 kilohertz and 5 kilohertz, and this is the porous blade. So both of these are getting noise at the tips. There's some dropout there, I'm not sure what that is, but on the tips. But the thing to look at is the dynamic range. This has got a top of 53, this has got a top of 38. So levels come right down. And if we look at the center microphone spectrum, so we can just pick one of them. So this is a fan running, it should be pitch angle, not angle of attack, pitch angle of 5 degrees, 700 RPM. So this is the reference blade, and this is a porous blade. So there's a band here that where we get very good noise control. Now this is I don't think we achieve, we're looking at 10 dB. I don't think you'd ever achieve that on a real turbine in a real situation at high Reynolds number, but we do think it's got merit to look at further. Oh, and this is a preliminary large eddy simulation of the same test case. So what we have at the top here, well, this is the blade, this flow, this is the turbulence, and here's some pores, and you can see there's turbulence being absorbed into the pores, actually, if you look at it very closely, it's very messy. You can see, especially at an angle of attack, there's flow going up and down in those pores. So there's dissipation in the pores, but also they're like microjets, and they're breaking the turbulence up either side. And that breaking the turbulence up, I think, has got a key role in reducing the noise, because the noise is not only dependent on the intensity of the turbulence, but it also depends on span-wise length scale. So if you've got an eddy that's very coherent like that, it's going to be much more efficient than a bunch of random eddies that are only half or quarter of its size. But that's it. That's all I got. So, there's some conclusions there. I'm not sure exactly what I'm saying here, but for the porous blades, we think there's a lot of a long way to go to optimise them and to look at very different designs, especially subsurface cavities, much longer pores that can go up into the body of the blade. With 3D printing, we can just try so many different designs. But what we need to do as researchers is understand the near-field physics really much more completely than we do now. So we're doing a lot more wind tunnel tests and a lot more exploratory stuff. We want to look at other things like gas turbines, because this is a big problem for gas turbines. And we are lucky enough to have a metal 3D printer about to be installed, so we can do metallic blades. And this could also be a good technology to control the turbulence interaction noise at the front of the blade, at the leading edge. Okay, so before any questions, I've got to thank the Flow Noise group, because they did all the work. I'm just standing here telling what they did, and especially to Branko, who's now at Flinders Uni. He built the rotor rig and did a lot of the array measurements, and he did holography measurements as well, so didn't present. Yendru, who's sitting here today, he did the simulations for his PhD. Jeffrey, he's a postdoc, he's carried on a lot of the array measurements, and he's doing, right as we speak, he's measuring the pressure of that interaction of the blade and the tower. Zeb, who also worked on the project a few years ago, he now works for industry. He built the array. And Xiao Yang, who's doing all the 3D printing stuff. And of course, I have to thank Australian Research Council, because they funded most of it. Okay, thank you. Hit me with the questions.
Thank you very much.
Yep.
Do we have any questions?
Thanks, Con. That was very informative. I'll probably skip over a few things, because I know a lot of the work that you talked about now was for probably use in turbines and blades that are in close proximity to receivers. Mm-hmm. But in my position, looking at wind farms, there's kind of a couple of things I take from your presentation. The trailing edge applications that you've been looking at are all in the higher frequencies. Mm-hmm. That's when they're most effective at reducing those. So really, for say a wind farm where your nearest receivers are 1.5 to 2 kilometres away, it's probably not going to be that useful.
Well, you'd have to talk with the developer or the designer of wind farms, or people who do the compliance stuff. I think it is important, because if you get too many together, you could have an audible component at 1.5. But I don't think I think 600 metres is about the normal audible range of these things. But I'm not that person.
No, but most of our issues of frequency are from because of atmospheric absorption and so forth.
Yes, that's true.
You don't really have a problem below about 630 hertz, above 630 hertz. Uh-huh. Most of it's attenuated out quite significantly.
Trailing edge noise will go down to below that for the 300 hertz region.
Okay.
On these big blades.
Then that would be touching into the areas of concern. But what I did take from the first part when you talked about it was the acoustic pulses you were getting going past the tower.
Mm.
And it would seem to me, to the best of my knowledge, that we don't look at how we might best attenuate those.
Oh, no, that's right.
And I guess that leads on to my question is, should we be looking at, and I'll ask you, that those pulses, are they really confined to the tip of the blade? Because we're looking at 60-metre blades. So when those pulses go past the tower...
No, let's see if I got the right figure. But the tower is the biggest noise source, and it's distributed over a fair distance of it. So,
But I guess, is the tower kind of excited by mainly the tip? 'Cause that's
no,
where you get the
well,
velocities.
I should have brought the full. Maybe Yendri can tell me. Where is he? Can you remember the extent of the tower?
If you play the animation, you can see the pressure is changing. Like
There you go.
there. It's not just limited to the tip.
No?
Yeah, but
See how big that is
Okay, so maybe 8 or 10 metres
on a real turbine,
on a 60-metre blade?
easily,
So
easily.
would that be an area that maybe we should look at how we could
If
attenuate that area?
that's the controversial thing. If the infrasound is a problem, so I don't know. Is it a problem? If it isn't,
It's not
but academically it's very interesting, and it's a good way to get rid of it is to change the shape of the tower, and to put sweep on the blade.
Yeah, would it be a change in the shape of the tower, or would it be possibly looking at some of those materials or those
Oh, yeah,
technologies that
You could put damping. Yep. You could put porous materials.
But to your knowledge, has that been looked at at all?
No.
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 Neither.
No, nobody's looked at that. No, nobody. Well, they do know now after we've done it, but the tower wasn't considered as a noise source. But nobody considered that the tower would have significant forces on it.
No, not since the days that we put the blades in front of the tower rather than
Oh,
behind.
well, when they were behind, that there was interacting with the wake, so they were a long way away from the tower. But now when they're front and they're reasonably close to the tower itself is generating a lot of load, and that's creating an acoustic pulse.
Okay. So that might be something that we might
Yeah.
talk further about.
Yeah, absolutely.
Con, you mentioned in passing that they tried sweep, in other words, putting the blades non-radially.
Well, that's an idea of ours, but they use that quite a lot in fans, and it works very well because you're spreading the load over time, so you're reducing its intensity.
Just going on from the last question, have you ever seen a rotor blade which has got a bit of a curve on it to try and?
To fix this. No, I've never seen.
Now, like a
that.
sickle.
Yeah, well, not as a wind turbine, but
No.
certainly
But that
a
might have
low-speed fan.
that might have
Of course, yeah,
an effect on that.
absolutely, yeah.
But putting a curved 60-metre rotor blade on a truck might pose.
That's right.
I've got one.
Or just spinning it, just the dynamics of that might prove challenging.
Yeah.
But that's why we're here. that's
Con, I have one more question. Most of the camera noise camera results that I've seen show that there's that most of the tip noise is created not evenly like you've got it, but on the downward.
That's right. Yep. That's because the most wind turbine phased array measurements are done with an array on the ground, looking up at the turbines, and then they just transpose their image onto that map. But what that means is that when the blade's coming down, that's got a higher noise source than a retreating blade, and it shows an asymmetric profile. But when we did these tests, we aligned the array with the centre line of this, so there's no variation, there's no convective amplification.
There's no variation as the blade goes around.
That's right. There's no acceleration or retreat towards the microphones. They're just spinning in a plane parallel to the array.
So you can agree with the suggestion that in a boundary layer flow situation,
Mm-hmm.
that as the blade loads up on its upswing, and then on its downswing it unloads.
Yeah, it is unloading.
Is that really a burpee? That doesn't happen?
It does, but
Doesn't create.
that would only change because that mean velocity profile is very slight compared. Like we're talking 10 to 5 meters per second, maybe across that rotor plane, but the tip's 60 meters per second. So that change isn't that important for trailing edge noise. Trailing edge noise is generated by the boundary layer itself, so that slight fluctuation isn't going to change the turbulence on the boundary layer so much. So that noise, when you see it higher noise source, if you're looking up at a turbine, this blade's going to seem louder there than it does there because it's coming towards you, convective amplification, and that noise source is got a directivity forward from the trailing edge. It's like a spotlight going forward. So there's two things adding up there. But the main thing is convective amplification because it's coming around, rushing towards you.
Any more questions?
Getting back to the tower blade interaction,
Mhm.
is there an optimum position of the separation of the blade from the tower?
Oh no, it just decreases the further you put it away. So the further you get it away from the tower, the better. But I guess there's all other mechanical design issues, cantilevering the rotor off the top of the tower.
Okay. Well, thank you very
Yes,
much.
my pleasure. No worries. Yeah, good.
I've never dealt with wind farm.
Yeah. Oh, good. Oh, good. I'm glad. Yeah, that's right. Thanks, Andrew. Thanks for all the results. Yeah, see you. Thank you.